Hello student, welcome to the second lesson on this chapter on limits and derivatives. In lesson 1, we studied the tangent and the velocity problem, which I had said at that time lays a foundation or gives an introduction or creates the ground for defining the two important concepts of calculus, the limits and derivatives. Okay. In this lesson, we will get formally into the concept of limits. Okay, so let us begin. To find the tangent to a curve or velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. Okay, now, what we did in the previous lesson, now we are doing formally, numerically and graphically. So this numerical part is like through a table or list of values, and graphical part would be by sketching the graph and observing what is happening to the function to see the limit. Let's look at numerically first. Consider this function f of x equals x minus 1 over x square minus 1. Okay, let me put it this way if it helps you understand. The x square minus 1 is in the denominator, x minus 1 is in the numerator. Now I will zoom in on the table of values. We have seen this pattern, previously also while trying to calculate the slope. As you get closer and closer to 1, the value of the function is getting closer to 0.5, right? You can see in the table. Similarly, if it is greater than 1 and you get closer to 1, the value of the function is again getting closer to 0.5, 0.49999, will become 0.5 eventually. What are we doing here? In both the sides, we are getting closer to 1. 1 is here. From both left and right, we are getting close to 1 in the domain, the x values, and we are observing the y values. Okay. So by looking at this pattern, what these arrows are showing here, ultimately, when x gets to 1, this is from left, that is the language we use. Okay. On this side, from left, and here, this is from the right. Okay, maybe you want to use the article the, from the left and from the right. As you get closer to 1, as x gets closer to 1, the function value is getting closer to 5 in both cases. Hence, you will say the limit is 5. How will you write that? You will write that, okay, let me write it here before going there. Limit as x approaches 1 of that function f of x, which is x minus 1 over x square minus 1, is 5. That is how we will express it. Okay. Let us see here now. Okay. Finding the limits numerically and graphically, phase 2. Graphically now, if we were to look at the graph of that function, it looks like this. Okay. And you might want to remember from college algebra that the denominator could have been factored here as x minus 1 times x plus 1 from pre-calculus studies, right? You cancel the x minus 1, you are left with x plus 1, which is the graph of the hyperbola. And hence that's what you are seeing here. This is the hyperbola, which is asymptotic to the line at x equals negative 1. This will be 1 over x plus 1 for x not equal to 1, right? X not equal to 1, and actually we should say and negative 1. Okay, 1 and -1, the function is not defined, but other than that, it acts like x plus 1. So it will be the graph hyperbola uh, with, actually the left side is not shown in this graph. We are focusing on the right side because we are looking at the limit as x approaches 1 here. Okay, this is one part. The other part will be on the left side, facing down. And the difference between these 2 points in the denominator, okay, where I was going to focus on is there are two terms in the denominator, x minus 1 and x plus 1. The x plus 1 gives rise to this asymptote here at x equals -1 because it still survives here. All of this from graphing of rational functions. You might have, you should have studied in pre-calc or college algebra. Okay, and that gives you the asymptote here, whereas the x minus 1 gets cancelled, right? The factor that gets completely cancelled gives rise to the hole in the graph. Okay, it is that hole where the limit is finite. Okay, and that hole corresponds to the y value 0.5 on the y-axis. Check that, 0.5. And although the function is not defined at that point, but it is getting close to that from both the sides, because other than that point, the function is just like 1 over x plus 1, right? So this will be what we call a discontinuity with a hole, right? And the limit of the function at that as x approaches 1, the limit is 0.5. Okay, although the value of the function is not 0.5, the limit of the function as x approaches 1 is 0.5. You could see it graphically as well. Okay, and this idea, whatever we have been discussing, is written like this in the language of limits. Okay, and how do we read it? The limit of the function f of x as x approaches 1 is equal to 0.5. We said it. Okay, and that what we say there, these quotes, what is in quotes in mathematical symbols, it's written like this. And whenever you have a limit written like that, that is how we read it. Limit of the function as x approaches 1 is equal to whatever the value on the right side. Okay. Now, coming to the definition of limit, first we get into the intuitive definition, okay, which we have seen an example just now. Function f of x will have the limit L, some finite number L, as x approaches a, right? When if you can make the function value close to that number L, that is called arbitrarily close. Okay, and the meaning of arbitrarily close is as close as we like. So if someone gives you a challenge, make the difference between the value of the function and the limit that you are saying is the limit, make that difference less than 0.00001, someone says, suppose. We should be able to make that. Okay, how will you make it that difference less than 0.00001? You will choose x such that, you choose x in such a way that x minus that limit, the point at which you are calculating the limit, that x minus 1 would be less than some 0.0000, some number. Okay, I'm just saying a random number here. So you make the difference between x and the point at which you are calculating the limit very, very, very small. Like in the table, we are taking values 0.9999, 0.99999, right? You can keep getting closer and closer to 1. And when you do that, at some point, you are so close to 1 that the difference between the value of the function and the limit is less than whatever you want. Okay. If we can do that indefinitely, that is what is meant by as close as we like or arbitrarily close. Okay. then you say the limit exists, and that number L is the limit. Okay, so this is the intuitive definition of limit. I hope you are paying attention and getting like a good understanding of these phrases that we commonly use in the language of limits. Okay, and another alternative way to write is this: fx approaches L. F of x approaches L as x approaches A. Okay, so that is to say that the limit of the function is L. Very important point is we never consider x equal to A. Here, focus on that. Okay, we never consider x equal to A. So as long as you are interested in the limit, you don't bother about exactly at A what happens. Just like in the function x minus 1 over x square minus 1, in fact f of 1 is not defined, right? Is undefined. Okay, but still we say the limit is 0.5, right? So the limit is about where the function is approaching to as you are on the left and right, never about what happens at 1. In this case, f of 1 is undefined. In some other case, you could artificially define that f of 1 to be something else also, or it could be the same thing as the limit. Okay, that is irrelevant. Okay, the only thing that matters is how is f defined near A. Okay, here is more diagrams to explain the situation. What I was saying, three things, right? The value of the function could be actually the same as the limit. Actually, we will be seeing it soon, so why not introduce it? This is when continuous. The function is continuous at A because the limit and the value of the function are same. The remaining two cases, the function is not continuous. Okay, but for different reasons. Here it is not continuous because the function is not defined at all. F of A is undefined. Okay. Limit exists. In all three cases, limit exists and is equal to L. The limit of the function as x approaches A is L in all three cases. Okay, in the first case continuous, second case function is not defined at A. In the third case, the function is defined at A. There is a value to it. Okay, let's say that value is some number m. So f of A is some number m, but that is not equal to L, where that L is the limit. Okay, limit exists and it's a finite number L. The value of the function is defined and is some number m, but that m and L are not equal. So limit exists. Okay, f is not continuous at A. Okay, all of this is at A. Okay, continuity we'll discuss more later, don't worry, but you are getting an idea here. Okay, here is a very good exercise. Guess this. Okay, now we are not asking you to prove it, or if you already know it, forget that you know it, but do the guesswork by not random guess, educated guess. Okay, what you will do is use a calculator, and as x approaches closer to 0, what happens to the value of the function? We look at the ratio and make a guess. Okay, in fact, I'm going to open a calculator and we will do some of it. Okay, here I have opened the calculator in radian mode, and I'm going to look at sine. We are getting close to 0, right? So zero point 0.1, let's say, divided by 0.1. Okay, that's 0.998. Okay, you might already make a guess here. Let's see if we are right. Take 0.001. Or what did you take? We take 2.1, right? So let's take 0.01 divided by 0.01. That's 0.99999. So I don't think I have to do any more. You can already see the limit is 1. Okay. By the way, that I took from the right. Okay, this is x approaching 0 from the right. You could do the other way around. Take minus 0.1. Okay, and divided by I don't know if this negative sign works. Here I think 0.1 negative. Okay, as I said, right? By the way, that should not be surprising, and I'll talk about that on the page here. Limiting approaching left and right is not a worry here because sine minus x over minus x, if you try to simplify, that's an odd function, right? Remember from the concept of odd and even. Okay, so it will be minus of sine x, hence ultimately it is sine x over x. Okay, so whatever limit it was approaching from the right, we knew that it will be definitely the same limit from the left side as well, and that is equal to. Okay, see, we could do this numerically. Now if you look at the graph, by the way, there should have been, yeah, there's a graph here. If you look at the graph, you see this, the graph of sine x over x. And you can see the limit is 1. Okay, you might want to remember that. I'll write it again here because this is a super important result in limits, and we at some point of time, I'm sure we are going to prove it. Okay, in calculus 1 or 2 somewhere you will prove it. Next we look at the concept of one-sided limits. Okay, and as we have seen in the graphs, and we can very easily imagine, sometimes a function might approach a finite value from one side but not from the other side. Okay, a typical example could be like this. Let me say, suppose this is an asymptote here at x equals 2, let's say. Okay, and what kind of function will have that asymptote? Let me write an example. Say a function f of x defined piecewise. That is the simplest way to get one-sided limits. Okay, suppose you define this function as 1 over x minus 2 for what? For x less than 2. Okay, and then you say that it is equal to simply say x for x greater than 2, right? And you can define it to be anything, but just not define it. Okay, you have this function defined, the domain of that function, in this case domain would be negative infinity to union to infinity, if you define it. Okay. Or I'm just discussing all different possibilities here. Okay, you could say the value of the function is x for x equal or greater than 2. That's also fine. In that case, your domain would be everything, all real numbers, if you define it. Okay, the x minus 2 would be the now hyperbola, right? And as x is getting closer to 2, the x minus 2, the graph, okay, I'm showing the graph here. At 0 it is negative 0.5, so the part of the hyperbola on the left side would look like that. Okay. And on the right side, it is equal or greater than, it's just x for x equal or greater than 2. So let's say this is at 2. So like that. The line y equals x, after that. And before that, it is the function y equals 1 over x plus 2. Now, if you approach from the left, it goes to negative infinity. So there is no limit. But if you approach from the right, you reach the value 2, right? So it has one-sided limit. Limit exists from the right, does not exist from the left. How would we write that in notation? We write like this. We say limit, okay, as x approaches 2 from the right. Limit as x approaches to from the right is indicated by writing a plus sign there. Of that function f of x is equal to 2. We say f of x equals x, so the limit will be 2. Whereas limit as x approaches 2 from the left of that function f of x does not exist. Oh, sorry, I made a mistake there. Don't write negative 1. Okay, 2 minus. Just the symbol minus. That would be x approaching 2 from the left. We write that as an exponent, but only plus or minus. Okay. What is the significance? Why do we write like that? Because when you are approaching from the right, the values of x are a little more than 2, right? 2 plus. You know, sometimes that is how we express our, even in um, common language, right? If someone asks like what's your height, and if I'm, let's say, at least I can dream, I'm 6 feet or taller, a little taller than 6 feet, I can say I'm 6 feet plus, right? You don't have to be precise. In the same way, plus is a little bit more than 2, minus would be a little bit less than 2. Now, one common mistake that I have seen students make is think that you are approaching 2 or you are approaching negative 2 or something like that. That is not the case. We write 2 minus, but that is not negative 2. Okay, it is 1.99999. Keep that in mind. Okay, all right. Here is that was my discussion. Let us work through the slides now. The Heaviside function h. Okay, and whenever we come across these functions through this course and some names are given to them, I would recommend that you remember them. Okay, try to memorize them. The Heaviside function h, these are some special functions with special applications in real world. How it is defined: 0 for t less than 0 and 1 for t equal or greater than 0. So this is something like, it is 0, 0, 0, like at this level, and suddenly from 1, like at a certain time, or whenever you start counting, maybe, it increases. Until the time you started, keeping track of it, because 0. Something like that you can imagine. Okay, that's a Heaviside function. And as t approaches from the left, by the way, I gave an example here where the limit does not exist from the left. This would be an example where limit exists from both the sides. Okay, but what kind of limit we will see. As it approaches from the left, it approaches 0. Actually, we will use an open 0 there to indicate that. Okay, and now I have to actually also draw the axis. That's x-axis, sorry, y-axis, and this is x-axis. Okay, and as it approaches from the 0, the limit is 0. As it approaches from the right, the limit is 1. Okay, so we write this here. I'll zoom in. As it approaches from 0, the limit is 0. As it approaches from right, the limit is 1. Okay, 0 minus 0 plus. These are called one-sided limits. Right? What happened in this case is the limit, one-sided limits exist from both sides, but they are not equal. So I'll go ahead and mention the next conclusion from here. The limit as t approaches 0 of the function s of t does not exist. Okay. So the two one-sided limits exist, but the limit does not exist because they didn't agree, right? They didn't agree on the same value from two sides. So you would say the limit as such does not exist. Okay, so value is less than 0, value is greater than 0. Intuitive definition of one-sided limits. By the way, this approaching from the left is also called left-hand limit, as you can understand, approaching from the left. Okay. And the intuitive definition here is similar to the intuitive definition of the general limit that we studied earlier. Now, only extra thing is you will put that condition that the number L will be the left-hand limit of the function f as x approaches a if for any arbitrary number that you give me, I can make the difference between f of x and L less than that number. How? By choosing values of x sufficiently close to a but less than a. That would be from the left. And similarly, the right hand limit by choosing values of x sufficiently close to a but more than a. Okay. And when would we say the limit exists from this perspective of one-sided limits? The limit would exist if both of these one-sided limits exist and they have the same value L. Then you will say the limit exists and is equal to L. Okay. If the left side limit is L and the right side limit is M and they are different, then the limit does not exist. If they both agree, then the limit exists. Right? This is the full picture here. Okay. And let us look at diagrams here to understand. Okay, so here for the left hand limit you are looking on this side, and for the right hand limit you are looking on that side, which basically means the graph what they're trying to show here is what is here. Nobody cares. If you are only interested in left hand limit, you don't bother about right side. If you are looking at right hand limit, what's to the left of that uh, value a, and what are the values of the function there, doesn't matter. Or even if that is not in the domain, doesn't matter. Okay, have that clarity. Okay, and here is the formal statement of what I was saying, a very important result, right? The limit of the function exists if left hand limit exists, right hand limit exists, and they are equal. See this if and only if part here. Okay, if and only if. Okay, here is an example graph, and we will try to find the values of all of these limits based on the graph. Okay. I will zoom in for you to be able to see clearly. We want to take a picture and we will get back to the questions. Okay. As x approaches 2 from the left, the first question is x approaches 2 from the left. Let us see here. As x approaches 2 from the left, the values are here, right? So the limit is 3. Yes, I should change the ink. And as x approaches 2 from the right, it's getting down here. The values are 1. Okay, go ahead, in the same way. As x approaches 2, now the two sides don't agree, so the limit doesn't exist. When it approaches 5 from the left, we're here. Okay, the value of the function is approaching 2, so the limit value is 2. As it approaches from the right, it's the same thing. Limit is approaching 2. Now the function is approaching 2. So the limit exists and is equal to 2. And I'll make the note here. Although f of, not f, g of 5 itself was equal to 1. Okay, limit is 2, although the value of the function is 1. Good. And here is the solutions, despite the fact, all of that you can observe. Okay, so which brings us to the question, we have been saying like limit exists and sometimes it does not exist. We have seen some examples. Let us like put everything together and list all possible situations where the limit does not exist. Now, why would it not exist? Before I turn the slides, let us recall. In one case, the function was going to infinity, right? Either on the left or on the right, if the values of the function go to infinity. If there is an asymptote, limit fails to exist. The other situation was the function has one-sided limits, but they don't agree, right? Basically, it's around this, okay? Left and right are exist but not equal, or either the left hand does not exist or the right hand does not exist. These are all situations where limit fails to exist. Don't look at the solution, just look at the question. Okay, investigate as x approaches 0 the limit of sine pi x. Okay, pi over x, not pi x. Okay, this is not sine x over x. If you are recollecting what we had discussed earlier, we had mentioned that limit as x approaches 0 of sine x over x was 1, right? Here the numerator is pi, constant. Now what happens? As x gets closer to 0, 1 over x or pi over x will become large and large. Recollect the graph of 1 over x. That's a graph of 1 over x on the left side and the right side. Okay, 1 over x. X-axis here, y-axis here. So as x gets closer to 0, 1 over x will be going to plus infinity on the right side, minus infinity on the left side. And when that happens, the values of the sign will be switching between 1 and minus 1, right? But how will this change? Very fast, because 1 over x is rapidly changing. It's rapidly going to infinity. So the values of sine 1 over x will rapidly fluctuate between 1 and minus 1. So what you will get is the whole graph of sine 1 over x, would be like this. If you now look at the graph of sine 1 over x, pi doesn't matter, okay? It's just a constant, it will only stretch it horizontally, but overall behavior does not change because of that. Okay, so the graph of sine 1 over x would be like this. For long values, like when you are at large negative x or positive x, the values will be close to 0. Okay, here let's say, but as it gets closer to 0, the values of the function will start fluctuating. It will be like that. Okay, it will be fluctuating and slowly it will die down and go to 0 again on the right side. It will become longer and longer and then 12. Okay, I didn't do a good job there, but you get the idea. Important thing is at 0, it will be very difficult to see. You will have to zoom in and zoom in and zoom in and see exactly at 0 the function is not defined. Okay, because this value usually not be defined. No, it's not in the domain. 0 is not in the domain of the function, but the function will be fluctuating between 1 and -1 so fast that the limit doesn't exist. Okay, that is the idea. Let us see how it is described in the book. If you plug in 1, you start from a little distance away. At 1, sine of pi is 0. At half, it is again 0. At 1/4, it is again 0. Okay, so that is the reason that chosen pi. Basically, it shows that at all of these values, the reciprocals of these integers, the value of the function will be 0. But between them, it will go between 1 and -1, right? So here's the graph, what I was trying to draw earlier. Okay, that's the classic, graph of sine 1 over x. And just because, okay, so what they said our guess is wrong is probably they just looked at the values at those integer values and saw that every time it is, at an integer value, it is 0. So you might say the limit is 0. But the point is, between those integer values, it was taking all other possible values between 1 and -1, right? So you're not getting a stable output. So the limit is not there. Limit doesn't exist. Okay, that's the conclusion. Okay, what are other situations? Infinite limits. So when I drew that one step function piecewise function earlier, uh, the conclusion was limit does not exist because it was going to infinity on the left side, and on the right side it was some finite, right? But what if, let's say, this is not the case, and on the right side also, if it is going to infinity, suppose if this was the graph, what would you say? You can always say limit does not exist at um, x equal to 2. You can say, like, this is the situation at x equal to 2, the limit doesn't exist. You can say that, or you can say that it is going down, which is it is going to negative infinity. So you would say limit x approaches to of the function. In this case, you would say negative infinity. Okay, and that is the idea of infinite limits. What is important is it should be going to negative infinity from both sides. Otherwise, you can only say that one-sided limit is negative infinity. And while we are on this, the another a simple example for this infinite limits is the graph that we have been using repeatedly, the graph of 1 over x. Okay, as you can see, limit, I'm writing, oh, let me write here, limit as x approaches 0 from the left of that 1 over x will be negative infinity. Limit as x approaches 0 from the right of that 1 over x would be plus n. Okay, so the two one-sided limits, each of them go to plus infinity and minus infinity. Whereas like this situation here, if from both sides it points to the same infinity, then we say the limit is that infinity, in which case we say infinite limit. And in all of these cases, there has to be a vertical asymptote, right? The existence of vertical asymptote is tied to the existence of infinite limits. Okay. What is the intuitive definition? what I showed you is graphical. The intuitive or the way to understand it is the values of the functions get larger and larger. That is the intuitive. Okay. How large? As large as you like. So if you give me a value like 10 billion, I have to be able to make the values of the function greater than 10 billion by making or by taking the values of x close enough to that number a, wherever you are saying the limit is infinite. Okay. I should make it as large as required, or if it is negative infinity, I should make it as large negative as required. Okay. We don't say small. Keep that in mind. Small refers to zero, both positive side or negative side. Large would be positively large plus infinity or negatively large negative infinity. Okay. Here some super important statements are used again here. The symbol infinity is not a number. Be careful about that. Although we write that, okay, we write this statement here. Limit as x approaches a of f of x is infinity. We write that equality here doesn't mean it's a number. Again, it is with a caveat. You have to understand that with a caveat. What we mean. Okay. This becomes infinite. I would not agree to that. Actually, I would say f of x tends to infinity. Becomes large or arbitrarily large. Increases without bound. Another good phrase actually to describe the situation. To describe the situation of x limit being infinity, you can say the function increases without bound. Okay, as x approaches a. We already talked about the infinite limits and vertical asymptotes. It doesn't have to be both sided to be the vertical asymptote. One common again misunderstanding is you think that only if it goes to infinity or negative on both sides you would call it a vertical asymptote. No, that's not the case. Even in the graph that I drew earlier, you would still call it a vertical asymptote. What was the graph? It was going to negative infinity here, but on the right side it was finite, and actually in fact it was touching that line. Okay. You would say, you can if you want to be more clearer, you can say the graph of the function or the function is asymptotic to that line from the left, just like limit. We can say asymptotic from the left, but you would still call that an asymptote. Okay. All right. And here about the function having negative infinity as the limit, and this is all reiteration of the same ideas. Okay. And here are some examples. When would you get a negative infinity as the limit? This is a situation. X approaches 0 and you are evaluating negative of 1 over x square. You have to understand, okay, what goes on here. X square will be positive whether x approaches from left or right. So 1 over x square will be large, positive, but then you slap a negative in front of it and it will be large negative now. So it will have that going to negative infinity situation. And other situations are possible. Okay. And one-sided limits can be defined. I think it's clear by this time. Illustrations are here, approaching to infinity from the left, approaching plus infinity from the right, approaching negative infinity from the left, approaching negative infinity. The function is approaching negative infinity from the right, okay, as x approaches a from the right. Okay. And when do you say the particle? If at least one, yes. So this is the clarification I was talking about earlier. We don't need both sides to be going to infinity. Okay, if at least one of them is true, any one side is going to infinity, then you have the vertical asymptote. Okay, here is an example problem. Find the vertical asymptotes of tan x. Now, if you remember the graphs of tan x, the domain range, you already know this. In fact, I mean, that should be a basic knowledge, okay? But in case you have forgotten or been a while, since you took either pre-cal or college algebra, here is an opportunity to review. Okay, what was that? Tan x is sin x over cos x. So where will I get the vertical asymptotes? Where cos x is 0 and sin x is not 0. But I don't have to worry about this. Why? Because sin and cos are related. Okay, they don't take independent values. So if cos x is 0, actually sin x will be 1 or minus 1. You don't have to worry. Okay, it won't be 0. So only thing I need to then do is find where cos x is 0. All right. What I said just now is important. Okay, don't it's not that I was simply saying something for the sake of saying. I will remind you this example earlier, right? Um, x approaches to 1 or minus 1, in both cases, the denominator will be 0. But when x approaches 1, it will cancel with the numerator factor and you will get a hole in the graph, not an asymptote, right? There is a hole at 1. Whereas only at -1, you would get that asymptote. Not at 1, but at -1. Okay. So it is important to check both. To get an asymptote, the denominator should be 0. Numerator either should not be 0, or if it is 0, when they cancel out in the reduced form, okay, if you cancel out all common factors, at the end, the denominator should be 0 and numerator should not be 0. Okay. And I was saying that for our current situation, we only have to worry about the denominator. The numerator is not equal to 0 is automatically applied. Okay. So close to pi over 2. Now we think, where is cos x equal to 0 when x is equal to pi over 2. X coordinate, right? Cos x is the x coordinate, which is 0 at 90 degree and 3 pi over 2 at 270. So as it approaches from the left or the right, you are going to have vertical asymptotes. And the general solution would be not just pi over 2, any odd multiples of pi over 2, like pi over 2, 3 pi over 2, right? 5 pi over 2, 7 pi over 2, and so on. So that situation is in general, defined as pi over 2 plus some n pi, and here are some examples. Pi over 2, 3 pi over 2, or negative pi over 2, negative 3 pi over 2, and so on. That is the graph of tangent. Okay, this pi over 2 plus n pi, there are two ways to understand that there actually. One is, there is a vertical asymptote at pi over 2, and the period of the function tan x is pi. This is all good review. Okay, period of tan x is pi. So after pi, after 2 pi, you will get this vertical asymptotes again. Another way to look at it is, if you combine that, you will get 2n plus 1 over 2 pi. Or you can write that as 2n plus 1 times pi over 2n plus 1 means odd number, right? So odd multiples of pi will be the vertical asymptotes. Okay, so that is the idea of limits. In the next video, I will solve problems on this topic. See you there. Thank you for watching.